I'm going to save it, and I'm going to add an AC analysis. In the AC analysis, I'm going to have a sweep from 1 kilohertz to, let's say, 1 megahertz. Make it simpler for the design, and then I want to have a decade logarithmic sweep, and I want to have at least 200 points, or even more, 500 points, to make it very sharp and accurate. Okay, now I put this thing, I defined the capacitors, and we should be good to go. Let's run the simulation. I'm going to go and analyze, and by default it actually would go for which value of K. So you double click on the imported Maxwell structure, and under the quantities, under the where was it? Yeah, it was under the quantities. You will find that the distance right now is 15, so you have to put it on 4. Okay, it will override the value to 4, and it will solve it for 4. Okay, the reason that it was 15 was because it was 15 by default in Maxwell, so it will basically grab this value. It doesn't care about a parametric sweep. So now if I say 4 millimeter, and it will override that, it will solve it for 4 millimeters. It will actually do exactly as if I was like selecting 4 in Maxwell. These are all connected. And I press OK here. And because it's already solved in the Maxwell, it shouldn't take that much time. Right click and then analyze. Okay, there we go. So now if I right click on results and create a standard report based on the frequency sweep, I want to go ahead on power, and I want to say, I want to see the output power. The output power is this one because I defined it as output. I just called it out, so it's here, it's called out. So if you define whatever here, you will see the same name here. WM means watt meter, and it will come anyway. Okay, now I want to say the efficiency would be the output power divided by the input power. Actually, these are the dB. I don't want to have it on dB, so I would go and say the magnitude divided by the magnitude of the input power. Okay, so everything is okay. Select on report, and you can see that it is resonating, but I'm now a bit suspicious that if the sides are correct. I'm gonna go on logarithmic. So you can see on 1 kilohertz you have exactly on 1 kilohertz you have this peak. So since the inductance is not changing that much, I just want to make sure that this is exactly the value that I want. So it tells you that the efficiency, because it's resonancing, it's actually pretty close to 1. It actually says 1, which is it should be a bit less than 1. Let me see. You double click on that to make sure that the numerical value is correct. So use the scientific way of presenting it, and there we go. In the scientific presentation, it's 99.999. So it's not exactly 1, but it's pretty close to 1. and you have two other adjacent frequencies that you can actually have this. Now if I go and change the distance instead of 4 to be 15, I'm wondering if 15 is one of my defined parameters, so I don't ask this guy to go ahead and redo everything. I know that 30 is one of them, so let's go and put it on 30. So it would not calculate again, it will already have the solution in Maxwell. So if I do that, and you can see that there's a cross on all of my results now, because now the environment changed. Now if I do the simulation, it should be very fast. There we go. Go ahead and update my report. So it's in 3 centimeters, it's 98%. But as you can see number of it's not exactly on 100. This is based on megahertz, so when x the frequency is 9.95, it's basically 99 kilohertz 0.5, and I think it is true because if you go to WPC website, you can see that in very in the magnetic inductance based or way technique of transferring power, you do not transfer power on exactly the same frequency as a resonant frequency. And I've got a better result before, and it will actually show you that on the resonant frequency you have a dip, and you can see here as well that there is a dip here on the resonant frequency exactly on 100 kilohertz, but that is not actually, oh come on, yeah, you can see the dips here, but that's not exactly what I was expecting to see. I was expecting to see a bit better result. It might be the exact result, but just in case, I want, because you might actually have the same problem sometimes, so I'm gonna do a rotate for that. First of all, I want to change it to exactly 4, and then I will rotate this to make sure that everything is fine. So you control X that, you cut it with control and X, and then you paste it somewhere else, and then you use this rotate tool, and then you rotate it twice, and then you bring it back to where it was, and then save it, and then analyze. And now if we check out the analysis, it might give you only, because it should be only one pick, it shouldn't have like more than one, unless if it's very low, very short distances. Update the result. What happened? There we go. That makes more sense. Although, oh yeah, now you can see that it's wrong because there's two, one here, one there. So the previous way was correct. So I'm gonna just go ahead and rotate it back to what it was, because it gave me. Can I show you guys again? So let me show you as a logarithmic view. What? I think I missed one of the open. That's, oh, okay. That's weird. Okay, now when you do it on the logarithmic tree, you can see here that you have two resonant frequency unit. That means that your CR and CT are not in the right place, or the terminals that actually it was telling you at the beginning was through terminology. So it happened once to me, so hopefully it never happens again. So as I said, to get the terminals, you just go to general by double clicking on that, and you can see in the table here that T1 basically representing RX1, T2 TX2, T3 RX1, and things like that. So again, I'm doing the simulation and analyze, and it should also update the result. Sorry for long boring tutorial this time. It's supposed to be shorter than that, but basically that's how you do that, and you can see that the result is pretty much what we expected. You have a pretty good coupling here. Well, no doubt, because the distance is like pretty small, so it's 99.99%, which is actually true, because I checked with WPC standard and they were like saying that in some cases you can get more than 99% of efficiency. Of course, we are not taking care of the quality factor of the coils. If the quality factor of the coils are poor, then you would not get that much of efficiency, and also we are measuring it purely with just no other parasitic components around. So if you're actually designing that, you will get not exactly 99.99%. You may get like less amount, but it's actually kind of surprising for me that the result is that good. For higher basically distances, I mean longer distances, you can see that this is not anymore the case, but still I was like thinking around like 94 or 95, but it seems to be a very perfect design, or we have a very good resonance, and that's probably why we get just changing the values to make sure that you see that everything is changing and the plot is not the same anymore. And if I zoom in, I should be able to see what is the exact. So here we get 98, and here we have 99.4. It's pretty good result. I think if you go higher, like around like 5 centimeters or 6 centimeters, you will see that it suddenly dropped to 60%. That's it. That's a tutorial for how you can get the power efficiency. I hope that it's useful for you and you get the answers that you were looking for. Thank you very much and have a wonderful day.